Hey, and welcome back. This is the second part to a series I'm doing on electric potential energy, and this is inside our electricity unit. And so hopefully you're a physics student or want to learn some physics here. This is another way of looking at electric potential energy. So stored energy based on position, dealing with electric charges. So if you imagine you have two positively charged particles over here, the question is how much potential energy do they have stored? Think about it. The closer they are, the more potential energy they have stored, right? And so there are some things to note about this version of the equation as opposed to the uniform electric field that we just talked about. So this form of the equation you can use with two charges, but you can also use with more than two charges and just add up the results. I'm going to show you how to do that later. We're going to start easy though. So this is our equation. One thing to note, down here I did write that note that this is an R value, so the distance between the center of both objects, and that's our R value right here. That's not an R squared, like Coulomb's law has an R squared, other equations have squared values down below, but this is just an R value. Another thing to note is that this would be a positive result if you have two like charges, and that's because it's tough to put them together. In other words, it would take work in the physics sense to bring these things close together. And so then it would have stored potential energy. That would be kind of like raising up an object up over your shoulder. It would take work to be able to do that, but then that object would have stored energy based on its position, which is similar to what we're talking about here, although not exactly the same. And last, like I said, I do want you to think about this as a system of particles. And so you can say, what is the electric potential energy of the system right here? How much stored energy does it have? Another way to think about this is if you release these two objects right here, they would repel each other and go moving away from each other, the object on the left to the left, the object on the right to the right. And so you could say, well, where does that energy come from? Because they would eventually have kinetic energy, right, as they move away. It doesn't just magically appear. That potential energy changes into kinetic energy. So this is another way to think about the system over here, as well as drawing in concepts of conservation of energy, which do apply here as well. All right, so let's continue and see how this works. All right, and so the problem that we have to work with here, it just says 2-point charges located on the y-axis. The first charge is a charge of 3.0 times 10 to the negative 9th coulombs, and is at the origin. The second has a charge of 6.0 times 10 to the negative 9th coulombs, and is at the points 0 centimeters, 30 centimeters. All right, our first question is, what is the electric potential energy between these two charges? So think about what you would do first for this problem. Take a couple seconds and visualize what you would do first. The first thing you want to do for a physics problem, especially if you're learning it's new or it's complex or there's a lot going on to keep track of, is draw a diagram. So that's what I've gone ahead and done here. And I'm including information from the problem in a sort of a word problem. It's going to be applied to the diagram itself to make it easier. And then I'm just going to take a look at my equation and write my equation down. So I have my equation already written down. Then I'm going to go ahead and plug in my numbers. And I solved for the answer, and I ended up with 5.4 times 10 to the negative 7th joules. Notice we're going to be using joules for our answer. Also notice I did change this value down here. This R value has to be changed into meters, even if it's given to you in something else. So it's given in centimeters, has to be changed to meters to get a standard-based answer. That would be joules for energy. And note also I'm going to label this as the electric potential energy between points 1 and 2. And I'm doing that because I'm going to build on this problem and make it slightly more complex so that you can see how to do a multi-charge system. Okay, and so if we take a look at part B, it says now what would be the electrical potential energy if a third charge is added with this amount of charge at the point 0, 60 centimeters. So I've gone ahead and updated my drawing here, which is something you would think about doing with the new required information. And I'm going to add to my drawing this, saying, well, I've already solved for the potential energy, the electric potential energy between 1 and 2, and I want you to take a moment and anticipate what you think we're going to be doing for this system of particles. To solve for the total electric potential energy for the system, how would we go about doing that? So think that through for just a moment. And so hopefully you're able to come up with the idea that we would go ahead and solve for the potential energy between these two right here. And then there would be one more logical thing we would have to do as well. What do you think we would need to do? Here we would need to also come up with the potential energy between these two charged particles. So there are three major interactions, so it's getting a little more complex here. And then after that, what would you anticipate we might need to do? What we're going to do after that is add up all of the individual interactions, the individual potential energies based on those charges, and add them up for a sum total and get the entire potential energy for the system. So that's what we're attempting to do here. And it's really not that bad. Once you understand the strategy and how to do it, the total potential energy of the system is just going to be the sum of the parts. It's like saying the whole thing is equal to the sum of the parts. And so we continue with the problem and do similar things to what we've done previously with different scenarios here. So we've got, this is the potential energy between 2 and 3 right here. This is the potential energy between 1 and 3 right here. And we essentially are going to be adding them together for our total, which is down here. So that is how you would approach one of these types of problems. And again, the importance of this is that you can have stored amounts of potential energy based on charges. This is something that drives your electronics, like the electronics in your cell phone is based off of these concepts. And I will say for electric potential energy, oftentimes you would do maybe a few problems on this or spend one day on this in a normal physics class and then typically move on. It's more of a stepping stone concept that's going to be very, very useful for something that's going to be incredibly important that we'll be talking through. I'm going to be doing more screencasts on that and other topics in this unit and in others. So if you like this, please like the video and please continue to watch. Have a great day.